So when we talked about molarity, so molarity was your relationship between moles and liters. And the reason we use molarity was why? Because what? Why? Why did we come up with molarity? What was our point? Sort of, because we could do mole or liters and grams for density. So why could we not use density? I'm getting at the right idea, because it's a solution. When we have a solution, it's now a mixture of two things. The density isn't going to be helpful because that's going to get us the density of the solution. Well, what would be in the solution? Water and whatever was dissolved in it, our solute. So that density conversion wouldn't get us a mass that's useful for a chemical equation. Right? So we want to use a new or create a new unit or conversion factor that would allow us to determine the amount of moles of substance present in the total volume of that solution. It's really just a fancy way of doing a concentration. We've seen concentrations in our, hopefully not everyday life, but have shown up in other situations, say like during spring break, right? You've seen concentrations show up before. Anybody heard of ABV? Nobody's heard of ABV, really? Nobody. Okay, as a hint, 21 and older, are there at least some people that are 21 and older, theoretically? Because then you should be able to say that you know ABV. 21 and under, you shouldn't admit it. And blood volume, hopefully, we wouldn't have to worry about. Okay. Alcohol by volume. So if you look at any kind of alcoholic beverage, they put an ABV on it, an alcohol by volume. Right? What they're saying is how much alcohol is present in the volume of the solution, or that entire container. So that gets you a percentage of the alcohol in it. We could use that information to help theoretically pace how we would be interacting with said beverage. Right? If you had an alcohol by volume that was 99%, or 99% versus 4%, your interaction with those two solutions should be very, very, very different, right? Right? One, you drink a little bit and it burns your mouth. The other part is like, I just don't like the taste of beer, right? Slightly different interactions, right? Why does alcohol use alcohol by volume and not molarity? When we use alcohol by volume, are we doing a conversion with it? No, it's really just a reporting of a value. We can then interpret that value and come up with our own approximations of how we might respond to said beverage. When we're looking at molarity, what's the point of molarity? To convert from one substance to another substance. Because we're trying to convert substances, we would need a chemical equation, and the chemical equation uses units of chemical equations use what units to convert? What's that? Moles, okay, or molecules. It's a counting unit. Alcohol by volume is not a counting unit. It's an actual measurement. Okay? It's the measurement of volume of the alcohol. It's a measurement of volume of the solution. Okay? Because we aren't doing a conversion, we don't have to stress as much about whatever unit system we use. Because we're trying to do a conversion in the case of molarity, we want to be a little bit more particular about what unit we pick, and that's the creation of the molarity. Okay? So when we look at this question, we might want to try and decide how we should solve this. Okay, so the first thing to do would be to what are we looking for? So identify what you're trying to solve. There's a lot of text behind that. Lots of information and lots of different pieces to piece together. Okay, what are we trying to solve for?
Molarity of nitrogen.
Okay. the molarity of the nitric acid. Okay, to solve for the molarity of the nitric acid, what do we need? We would need the moles of nitric acid and the liters of the solution of nitric acid. So we could go back through our question to see if that information is provided. What we will find is the liters of solution is provided. Right? However, the moles are not. Okay? At least not explicitly. Okay? So at this point, we'd have to recognize how would we get the moles. Well, the moles of nitric acid are going to come from... No, the periodic table gets you what? Close, grams per mole. Okay? Not just moles. Okay? So if we piece together the rest of this kind of problem, we notice that we are being asked about nitric acid. Are we being asked about another substance? Or given information about another substance? Barium hydroxide. And in fact, as we go through and read this question, it is stating that I'm reacting barium hydroxide with nitric acid. Right? And at an equivalence point, I know that those two things cancel each other out. Okay? Which would be after a chemical reaction. So if I knew the moles of barium hydroxide, what could I then determine? The moles of nitric acid. Okay? So in this process, we've got lots of little intricate pieces moving through it. Okay? I'm going to need to recognize that there's a chemical equation or a chemical reaction. What chemical reaction is that? It's nitric acid, which should be a big hint. It's a neutralization reaction. Okay? To do the neutralization, I'm going to need reactants and products, right? Okay? Am I given formulas for a chemical reaction? No, so what would I have to do? I would have to write my own formulas using... How do I come up with my own formulas? Nomenclature. So I would have to use nomenclature to predict what those starting materials were. Once I have nomenclature for what those materials are, I could then predict products. Why would I need to predict products?
You can have your products, so you can compare them.
So I can compare what? Do I need to compare to the products? I need a balanced equation so I can compare nitric acid to barium hydroxide. Okay, so I do need to be able to predict products, not because I'm trying to determine how much products I'm making, but so that I can get the correct mole ratio between nitric acid and barium. So once I predict the products, then I can balance the equation. Once I've got the equation balanced, that gets me a key piece of information. That gets me the mole-to-mole ratio, which would allow me to convert, thank you, between nitric acid and barium hydroxide. Okay? As moles. Am I given moles of barium hydroxide? Where does it say moles of barium hydroxide? It says molarity, which is capital M, which is moles over liters. So it gives me a unit that I could use, but now I'm going to have to create my unit conversion. Okay? And I'm only saying it's only 3 steps. It's not that bad, but each of those steps has individual pieces that you have to go through and process. Your unit conversion is going to end up trying to convert the moles per liter of barium hydroxide into the moles of nitric acid. To be able to do that, what am I going to have to do? Do I want liters? No, so I'm going to have to cancel out the liters unit. Am I given liters? I'm given milliliters, so in the process of canceling liters, I'm also going to have to do a conversion from milliliters. Okay? Now I've got the liters canceled, but I'd have moles of barium hydroxide. Do I want moles of barium hydroxide? No, so I have to do a mole to mole conversion. Where's the mole to mole conversion come in? That's the balanced chemical equation. Okay? That would now give me my moles of nitric acid. What could I do with the moles of nitric acid? I can take that all the way back to my initial step where I outlined what I needed to get. I needed to get moles, and now I can take moles over liters of my solution of nitric acid, and I'd end up with my answer. Okay, simple. Okay? Lots of intricate steps behind this. You need to be trying to work through this to figure this out. Okay? I'm intentionally not going to go through and show the work for this for two reasons. Okay? Number one, I want you to struggle through with it, and if you have questions, you should ask. Okay? So what you can do is write it all. Sorry, I appreciate the surprise. I want you to write out that work. Take a picture of it, send it to me. I'll give you feedback on what I see. Okay? Or show up in office hours. Okay? Ask me there. I got stuck here. I couldn't figure out what to do. You've got a rough outline of all the individual pieces that you need to go through and process. There's lots of pieces. Okay? This one question covers everything we've talked about this semester. Okay? So it is an insanely difficult question in that respect because it has a lot of moving pieces. Any weakness at any one of those points and the whole thing crumbles. When you move into 151, this is what you're expected to do for virtually every question. Okay? In 130, we wouldn't ask you this very often. Why not? We, in my opinion, shouldn't ask you this very often. Why not? If you get this question wrong, why did you get it wrong? I have no clue why you got it wrong. Okay? There's so many different moving pieces behind it. You could have gotten it wrong because you don't know conversions. You could have gotten it wrong because you don't understand nomenclature. You could have gotten it wrong because you don't recognize the neutralization reaction and what the product should be. There's so many intricate moving pieces behind it that at the Chem 130 level, we aren't trying to see, can you put all of those pieces together all at once yet. We're really trying to focus at each of those individual pieces. What I want you to see is where we end up. Okay? You can fully expect a question of this level to show up on the exam once. Okay? What do you think? Multiple choice or show your work? Show your work. Okay? This way I can see where you made a mistake and I can deduct from there. Okay? Make sense? The more work you can put down. Notice, did I actually solve it? No. Did I show that I could solve it? Yeah. Okay? I may not know how to do each of those pieces, but I know those pieces are important. By specifying that information, I now put the onus on the grader to be like, I'm going to take away all your points because you didn't actually show any work, or you showed me that you could do it, you just didn't. Okay? Should you get points? Okay? Defensible positions. Make sense? Ish? Okay. That is the end of our molarity discussion, which kind of gets us, okay, into what we're doing. Okay. Conversions. What I'm trying to get you to do is dimensional analysis. Okay. I'm talking to multiple people in multiple classes that saying, well, isn't there an equation to do this? Yes, there's an equation to do everything in the world. The problem with those equations is you have to memorize them. Okay. The beauty of dimensional analysis is there isn't a memorization of an equation. It is a process that allows you to do multitudes of different things without having to memorize an equation. Okay? If you would like to memorize equations, that is on you. You can create your own equations. You can look them up. You can find them. You can do it. Okay? I will get, oh, I just need to divide by 6.022 times 10 to the 23rd. And I'll be like, I have no idea if you're supposed to divide by it or multiply it. Okay? I literally don't know. I have to write out the work. Okay? The same thing happens for really stupid conversions, like inches to feet. Okay? I screw it up all the time when I talk about it because I don't have an algorithm. I've literally removed the memorization process from my brain so that I can write it down. Okay? That written process allows you to solve accurately all the time. Because I know my brain is a scary, scary place to be, and I don't want to do any work inside it. Okay? That's ultimately where I would like you to get, to acknowledge that you are a scary human being, right, and that you need to write things down and become less scary. Kind of make sense? Okay, so in our conversions, our general format, okay, we start with step 1. What do we want? Okay, our desired measurement and substance. Together, the measurement and the substance make the, what do they make? Okay, molarity would be a specific example, and even then, the molarity didn't specify the substance. Unit. This gives us our unit. Okay, units must be canceled as a whole part. Okay, I can recognize that when I go back to step 2, looking at the given measurement and substance, come on, reconnect, 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 thank you. What I can do is break that unit down into component pieces. I can recognize that there is a measurement and a substance. And I can compare step 1 and step 2 and say, did the measurement change? Did the substance change? Okay. That gets me an idea of what I need to do in that individual conversion part. Okay. But as a unit, I have to cancel the whole thing. I can't cancel parts of it. Kind of, sort of? Okay, so that is our basic process. Okay, step 3 gets repeated until we've made those two sides equal to each other. And that is our general format. That's all we're trying to do. Okay? So, converting A equals to convert B. Okay? So the numerical relationship between those. Okay? Why is it given in the equality and not as the fraction shown above? So if you looked at the front of the exam is going to show you this thing. Why does the front of the exam show this and not this? Okay, it can go either way. The equality allows me to choose which one do I want. Okay, it gives me more freedom. The fraction is now locked in to only one conversion. Okay? To get the fraction, what do we have to do? How do I get the left box, the lower box to the upper box? I divide both sides by b. Okay? By converting both or dividing both sides by b, what happens to the right-hand side? That now becomes 1. That's why I can insert it into the equation, because all I'm doing is multiplying by 1. Okay? That's kind of the mathematical reason behind it. Make sense? Okay. So, what are some conversions? What's that?
1 foot equals 12 inches.
Cool. So we could say 1 foot equals 12 inches. What other conversions you got?
1 meter equals 1,000 milliliters.
Nothing? You got nothing else? No other conversions? Wasn't like a conversion factor that you were told to memorize? Okay. 1 mole equals 6.022 times 10 to the 23rd items. Anybody else want to put out a conversion factor? Say that maybe we just talked about. Begins with a capital M. Molarity. Moles equals moles equals, what does molarity relate? The moles over liters, which would be volume. So this conversion is moles equals volume, or liters. Okay? What is wrong with all of these conversions? Nope, equation's fine.
They look like they're functions, like convert A equals convert B, they all look like that, or something like that.
Sort of. What is A in the first case? Let's take a look at this first one.
One B, B,
Feet, I would argue. And then what is B? Inches. The numerical value is the thing associated with those two units. Okay? So it does fit that pattern. We're converting feet to inches. Okay? All of these have a massive flaw.
they're inconsistent.
No, they're all pretty consistent in our formatting. Okay, we could go through and say that last one, we don't have any numbers. Why do we not have any numbers for that last one?
That's assumed that they're both one.
Nope, they aren't assumed that they're both one. This is the amount of moles dissolved in a solution. Can I change the amount of moles dissolved in a solution? Yes. It depends on the solution. So why are there numbers not written for that last one? It depends on the solution. Okay? Every solution is going to have a different amount of moles dissolved in it, which means those numbers could change. Typically, when we look at it, we like to keep our numbers with the thing in top, and it's typically moles, so it's almost always 1 liter. Okay? But that would then just be the last one, not the other ones, because the other ones had numbers associated with them. So what's wrong with all of these? Would you like another hint? I mean, they're big, vague questions. You
Sure.
want a hint? Okay, here's a big hint. Let's take a look at the red box.
It's just measurement, not substance.
All of these conversions are just the measurement. Okay, we have to be very careful in chemistry, because in chemistry, we're largely trying to convert substances. So we need to make sure that the substance is included with the unit. Okay? Why is it hard to include a substance with each of these units? Just like with the molarity, it's always different. Depending on what our substance is, it could change. Okay? So if we think it could change, we could say feet of A, inches of A. Why does it have to be A?
He's the same substance,
What did we change?
just measurement.
We changed the measurement. If we change the measurement, what has to happen to the substance? It must stay the same. Okay? So we could go through each of these and specify that extra substance behind it. Okay? Notice in all of these, we're going to have the same substance all the way through. Why would we have the same substance all the way through? No, not necessarily. So why do all of these conversions going to have the same substance associated with them?
Because you have the converted substances yet?
So they can all be converted with each other.
When can you convert substance?
Balanced chemical equation.
True. What is your measurement unit? Moles. Why are these all the same substance?
They're not mole.
They're not mole to mole. In each of these cases, what are we changing? We're changing the measurement. Can we change the substance if we change the measurement? No. So all of these are going to be the same substance. Okay? Where did these conversion factors come from? How do you know 1 foot is 12 inches? You memorized it. How do you know 1 liter is 1,000 milliliters? Which, for the record, bothers me. I'll come back to that one in a second. How do you know 1 liter is 1,000 milliliters? You memorized it. You were told to memorize it. How do you know 1 mole is 6.022 times 10 to the 23rd items? You memorized it. Moles to liters.
Should be 1 milliliter is 10 to the negative third liter.
Moles to, and that's a separate question. Moles to liters. Memorized? You memorized that the number of moles is 1 liter? Where do you find the mole? It's given to you in the question. So recognizing when you're supposed to have these memorized versus when you're supposed to find it in the question is an important thing to identify. You should always check the question to see if that information is there. Okay? For the record, let's go back and look at this one. What does milli mean? 10 to the negative 3. Where's the power of 10 always go?
With the
Base.
core unit.
With the core unit. The core unit is liters. Those are identical conversions. Whichever one you use consistently, I'm cool with. Okay? So you need to be aware of these conversion factors, where to find them, how to manipulate them. The how to manipulate them is our general pathway. Okay? But you have to start remembering how to pull them out. Okay? The feet to inches, the liters to milliliters, ultimately those conversions aren't as useful in chemistry. Why aren't they as useful? What is your end goal in chemistry? To get a grade so I can stop taking it.
Reaction,
A reaction. What is the point of a chemical reaction?
blow shit up.
Not quite. To get a product. Where are you getting the product from? A reactant. What is the point of a chemical reaction? To convert one substance to another substance. It's a substance conversion. What is our units for substance conversions? Moles. Why are the first two not as relevant? They don't have anything to do with moles. Why are the next two tend to be more important for chemistry? They involve moles. Okay? So one of the biggest important conversions that you need to manipulate through is moles, because that's chemical equations. Okay? So depending, that sure seemed to shift suddenly. But yeah, I guess that's it. Okay? Is looking at recognizing how we can convert from one substance to another. That conversion is centered right there in the middle. Okay? How do I find that conversion? How do I convert one substance to another? A balanced chemical equation. Okay? What if I'm not given moles? What if I'm given atoms or molecules? How would I get from atoms or molecules into moles? Okay? I could use the periodic table to do that interpretation. Okay? I could also go atoms to AMUs. How do I do that conversion? That's our periodic table, because our periodic table gives us AMUs. It also gives us grams to mole. Okay? So we can look at individual conversions to set us up in each of those stages. If you go through and use what the Tutor Center has put together, they've got a theoretically prettier version of this. They call it the mole wheel, and it's a giant death trap of spiky, sharp things coming off of it. Okay? Ultimately, what that thing is doing is showing the same idea. How can we move from one unit to another unit, and where do we find that conversion factor? Okay? Arguably, the most important conversion factor, in my opinion, is sitting right there in the middle, your balanced chemical reaction. You have to have it balanced for it to be valid. You have to have correct products for it to be valid. So you have to do everything from Unit 2 to predict that equation. Once you have that equation, it's now just a question of using that conversion factor in that process. Okay? And that's why this particular unit becomes more challenging than the last one. The last one, you were given conversion factors. This one, you have to find them. Okay? You have to interpret where that information is found. Kind of, sort of? Okay. Another idea on a separate way to find where our conversion factors are is number of atoms. Your formulas tell you the number of atoms. Okay? Number of molecules. So you can relate molecules to each other from a balanced chemical equation. You can do moles. Moles are just a very large number of atoms. So you can get that information from formulas and equations. You could also get it through using Avogadro's number. Okay? If you're given a large number of molecules. Atomic or molar mass, depending on what you're trying to look at. That was a fun little typo there. This is AMU per atom, okay, or grams per mole. That information is found on the periodic table. So you have to be able to look at the given information and decode some of that information out to get a conversion factor that allows you to convert processes. Kind of, sort of? Okay. It requires practice. Keep doing the practice. You got 2.5 weeks, 2 weeks? Okay. Which gets us to the next one, chapter 10, gases. Okay, gases is a bit of a weird one for us, and it's weird because it's sort of in our competencies and it's sort of not. Right? So we're required to talk about gases, but in a weird, loosey-goosey kind of term. Right? Most of the gas information is relatively straightforward, but there end up being some kind of hiccups. So, properties of gases: variable shape, variable volume. Okay? Remember, the gases want to constantly move away from each other, which means their shape is going to be composed by whatever container holds them. And then the volume of that gas is also due to the container. Okay? So their shape and volume are all over the map. Okay? They will expand and compress uniformly. Okay? If I have a cylinder and I push down on that cylinder, all the gas particles move down. If I tried to push down on a liquid, what's going to happen? Okay, the liquid will move in one place because we can't push uniform, or we don't push uniformly as easily, and the liquid will shift and wobble on us. Okay, so gases will do it nice and evenly. Very low density. Why would they be low densities? What is density? Mass in a volume. It's the conversion factor between mass and volume. Why would gases have a very low mass per volume ratio? You can't just say it's a gas. That's cheating.
They don't have a lot of mass.
Okay, why do they not have a large mass? What are you suggesting?
Because their volume is variable.
Close, not quite. Why would the volume be variable? In that picture, what do you think we're looking at? Solid, liquid, or gas? Gas. Why do you think it's a gas?
Because there's not a lot of particles.
There's a lot of space in between. What is that space in between? How would I measure, I don't know, say the volume of that space in between? Oh, a volume. Yeah, that's exactly right. What's in that volume? Okay, let's try that again, because that's kind of a weird question. So everybody see the red circle? Let's fix that, because I'm going to get somebody being a smart aleck on that. See that red circle? What is in the red circle? Nothing. Nothing but empty volume, which means the volume for that shape now goes up, but is there any mass in it? No, so the mass stays constant, which means I get a very large volume because it's mostly empty space. Right? So if I look at a density, where the density is calculated by mass over volume, but for a gas, what can I say about the volume?
Very high.
It's a very large volume. What happens to the density? It becomes smaller. For those of you that have problems with that, I had a lot of spatial reasoning issues with that. Okay? We're just saying what changes. Right? So pick a mass. What's a good mass to pick? Rhymes with fun. 1. Okay, well, I have to have something. Okay, so 1. Now I want to pick a volume. Let's pick 10. 1 over 10. Okay, what does that become? 1/10 or 0.1 as a decimal. Let's make a bigger volume. What volume do you want to pick that's bigger than 10? 100. What does the answer become? 0.01. Which of those two numbers was bigger? 0.1. The smaller the volume, the larger the density. The larger the volume, smaller the density. What is the relationship between density and volume? Inversely related. The bigger one gets, the smaller the other one. The bigger the other one gets, the smaller the other. Okay, it's an inverse relationship. Okay? Gases mix uniformly with other gases in the same container. Okay? This is kind of an assumption that we're making, and it works pretty well. So that if I take two gases and I put them into the same container, they just mix. Okay? Why would they mix uniformly? How much white space is there? Lots, which means the gases are just going to move constantly through each other since there's no white space, and they will mix as a uniform solution. Can I expect that to be true of liquids?
No.
Why not?
Because different densities.
We could look at different densities. How much white space is in a liquid? Very little white space. So for them to mix uniformly, what has to happen?
Like most of the same stuff.
They each have to slide by each other, so they're constantly interacting, which makes it a more difficult solution to mix. Gases, because there's tons of white space, odds are they'll just move right by. They won't even see each other. Okay? The next thing is gases do exert a force on their environment. Okay? I can't see a gas, yet I know it has a force. Why?
Atmospheric pressure.
I kind of understand where you're going with that one. We could be easier than that. How do I know gases exert a force?
Because the hotter
Anytime you
it
ever
goes up.
blow up a balloon,
Okay, when you blow up a balloon, what are you doing? What are you putting into that balloon?
Air
Gas. And what happens to the balloon?
changes shape.
It changes shape. Why is it changing shape?
Because you're forcing
Because something is forcing the shape to change. What is that something? Gases. Okay? So gases do exert a force on the container in which they're in. Okay? So what you ignore that. Okay? Ideal gas behavior. So before we get into what that force is, let's talk about some of the behaviors behind them. Okay? Not all substances act perfectly. We could go through and say the perfect human being won't go through and kill other people. Okay? Right? Everybody hopefully agrees with that statement. The perfect human being does not kill other people.
Have you seen the newspaper?
I'm not asking about real human beings. I'm saying the perfect human being. A perfect human being does not kill other people.
Right.
Yes.
Good. We should all. You guys are a bit slow on that one. That makes me a little nervous. The perfect human being does not kill other people. Okay? Yet, when we look at the real system, are there human beings that kill other people?
Yeah.
Yes. Okay? So we have this issue of an ideal system and a real system. Okay? And they don't necessarily agree. Okay? But if I'm going to try and base my life off of those, am I going to base it off of the one-off weird exceptions?
No.
Why not?
Because that's
If I said all human beings killed other people,
a generalization.
it's a generalization. We could work with that. What else would be the problem if we said all people try to kill other people?
All people wouldn't exist.
You're getting real generally. We don't have to go. You can get specific. Would I be in this room surrounded by 40 other people that want to kill me? I probably would not teach if that was my general philosophy. If that was your general philosophy that everybody was trying to kill everybody else, what the hell are you doing in this room? Okay? So we don't base our assumptions off of the outliers. We base our assumptions off of the general populace, okay, or the average. And we try to build an ideal system. Ideally, this is how substances act. Okay? Why would we mirror that? Well, it allows us to exist somewhat normally in the real world. Mathematically, when it comes to chemistry or physics, we want to mirror kind of the standard easy populace, because what does that do to all of our calculations?
Easier to predict.
It makes them easier. Okay? It can take something that is vastly overcomplicated and simplify it down that under most circumstances it works well for what I'm trying to do. Okay? So we create the ideal gas behavior. Okay? And we use that behavior to help us come up with mathematical models that explain the action of gases. Okay? Some of these behaviors are more valid, or not necessarily more valid, okay, are easier to understand and manipulate than others. Right? So number one, Gases are made up of super tiny molecules. They are so tiny, they have no volume. Okay? When you came into this room, where did you sit? In a chair. Did you sit in a chair that was already occupied by somebody else? Why not?
It'd be awkward.
Go with awkward, sure. Okay. Is that someone else taking up a volume? Yeah, so if you're the first person in this room, the volume of the room is the entire space. If you're the second person in, is it the same volume? No, the volume has changed depending on the number of particles present. That means if I change the number of particles, my volume changes, I would have to put that into my mathematical expression. Is that going to be a fun thing to interpret? No. So what do?
Gases have no volume.
I say they don't have any volume. Okay? That way I don't have to worry about that mathematical manipulation. Is it a decent approximation?
Sure there's a lot of white space.
There's a lot of white space when I look at a gas. Okay? So the odds that any individual gas particle is in the even attempts to be in the same space as another particle is very, very small. Okay? So probability would say that's not a horrible assumption, as long as there's a relatively limited amount of particles present. And I know that to be true because it's a gas. If I put in a whole bunch of particles in a tiny volume, what would I have? I would have a different phase. I'd move to a solid or a liquid. Kind of make sense? Okay. Gas molecules demonstrate rapid motion in straight lines and travel in random directions. This is not an easy one to manipulate or see how the mathematics come into it, so we'll just kind of accept it. Okay? Really, this is what's saying is that if a particle is moving in a straight line, what does it do? It keeps moving in a straight line until it hits something, and it exerts a force on that something. For every action there is
Equal and opposite.
an equal and opposite, and the thing will bounce back, okay, or pass straight through it. Okay.
If there's more heat, doesn't that happen a lot quicker?
We can address that, but we aren't there yet. That's actually at the bottom of this. Okay. Gas molecules have no attraction for one another. Okay. What was that? Just a sad murmuring? Yeah. Gases have no attraction for one another. Why might this be important?
You constantly be having reactions if they weren't.
If they're attracted to each other, they could potentially form chemical reactions. That's also going to do what to our other assumptions? If each particle has no volume, they can exist anywhere in the same space. If they're now attracted to one another, what are they likely to encounter? Each other, which means there's now a potential volume change because those particles are all collecting to one spot. Okay, so it would start to invalidate the other assumptions. Okay, so we make the assumption that there's no attraction for one another. Complete randomness. Is that true in our everyday experience? How many of you have been sitting in the same seat since you started class? Oh, interesting. Okay, why is that? If it was completely random, you should be in a different seat every class. Okay? You all have varying levels of, and I'm going to put attraction in quotes, because the attraction we're talking about is not like the human attraction. You have different attractions potentially for the instructor or the board that you're looking at. Okay? You may have decided that you need to sit closer so that you can see the board, or that you can hear me speak, or you need to sit further away because you're afraid that I'm going to throw stuff at you. Okay? I haven't done it yet. You should move forward.
What was that handling that you just did with them earlier?
Touche. Okay. Continuing, gas molecules collide without losing energy. Okay. That means when they hit, they completely bounce off. Okay. Kind of like pool balls. They hit each other and they ricochet perfectly off. If they didn't ricochet perfectly, what would happen? They're going to stop moving. They're going to change their energy. You can start to get now attractions for other particles. You're starting to collect things, and that becomes problematic. And then the last one, which is what Jesse was getting at, the average kinetic energy of a gas is proportional to the temperature. Okay? And the temperature is going to be in kelvins when we're looking at this. Okay? Meaning, the hotter it becomes, okay, the more energy, the more it can move. Does that make sense? What happens if I take a solid and I heat it up? It melts and becomes a liquid. What is that liquid doing different from the solid? It's moving more. What happens if I continue to heat it up? It becomes a gas. How is the gas different from the liquid? It moves even more. What if I continue to heat it up? It's going to continue to move more and more and more and more. So, could the volume change as it moves more? Well, if it's moving more, it has more energy. If it has more energy, right? I wouldn't do this, but you know, if I went up and hit a student, you know, gently, what if I hit it with more energy? I could get fired. The different response, right? Okay. Depending on the container, that container may absorb that shock, okay, and not change the volume. Or if it's, say, like a balloon, what happens? It expands until eventually it pops. So the more energy you put in, you can change the volume, but it depends on the container. Okay? So, all of these together come to this silly, stupid conversion factor. Right? And I can't stress that enough. I find this conversion factor insanely offensive. Right? This is brought up in chapter 8 as a conversion between moles and liters. Moles and liters. Didn't we have a conversion factor for moles and liters? Yeah, what was it? That was molarity. Well, why can't I use molarity for this? What is molarity for? A solution, effectively a liquid. Is this a liquid? No, this is a gas. So I would need a different conversion factor because it's a different phase. Okay? So that's why I don't like this, is that already students will start to use this to convert volume in moles. Okay? It's a bad idea because it only works for gases. Why might I be further irritated that this gets thrown in there early on? Which do you work with in the lab? How many of you have done a gas phase reaction? How many of you have done an aqueous phase reaction? Every single one of you should be raising your hand. Every experiment you've done involved water. You've all done aqueous phase reactions. And yet the first conversion factor to convert moles and liters that shows up in our textbook is for gases. Something that you will probably never use. Okay? So I find it insanely irritating that it shows up for that reason. So it only works for gases. It does not work for solutions. You don't work with gases. Okay? So it's bad for that reason. The next part of it. Okay, let's just look at what it says. 1 mole of any gas. So that's cool. It's any of them. So it doesn't matter what the gas is as long as the gas. Iron gas is going to occupy 22.4 liters. How am I going to get iron gas? Really hot. Because iron is a metal. We can do better than that. A solid. So I'd first have to heat it up to become a liquid, then I have to heat it up to become a gas. If I could do it, it's going to be 22.4 liters. It would probably destroy whatever container it was in, but hey, it would be 22.4 liters. Okay? So, cool. Why is that a big deal? Is that all that's in the red box? No, what's in the red box? When and STP, standard temperature and pressure. So this is saying we have this equality. 1 mole of any gas in the world equals 22.4 liters, except you have to be at this temperature. The instant you throw an exception in there, that's a horrible system to memorize because there's exceptions. Okay? Well, maybe temperature and pressure aren't things that change all that often. Yeah, temperature changes a lot. Like summer, winter, that's kind of a big deal. Pressure, does pressure change?
Yes.
Yes, it's not quite as bad, but pressure at sea level versus pressure in Flagstaff is different. Flagstaff. I had to make sure I got my directions right. Is different. Okay? How do we know the pressure is different at those two locations?
Air quality.
Yes, but that's a kind of convoluted one. What? what about the air pressure? How would you see that the air pressure has changed? And maybe Flagstaff isn't high enough. Maybe you have to go to Denver or Lake Tahoe.
You don't have oxygen in there.
Okay? You could look at the breathing. There's less oxygen. Anybody tried to cook?
Oh, yeah, bake,
Oh yeah, you try to bake at those altitudes, everything changes. Why?
because you have to make it longer.
Okay? You've changed the pressure, which means the point at which you're doing whenever you're baking is ultimately, what does baking do? It's the whole baking process.
Rising.
Why is it rising?
The heat.
What's causing the heat? What is the heat doing in your baking?
Expand.
What's causing it to rise? We can get into chemical reactions and we could use CO2 and all that, but arguably it's even simpler than that. The whole point of baking, or really any cooking process, is boil water. By boiling the water, it turns into a gas and it moves up through your substance. If it's bread, as it moves up, it creates air pockets. Okay? We reduce the amount of water present in a controlled fashion and we make a nice substance. If we want more air, that's where we're going to add baking soda and all that other stuff to give us other sources of air to give it fluff. Okay? When we go to a different altitude, we're changing the boiling point of the water, which means instead of boiling at 100 degrees Celsius, it boils at, it actually drops lower. Okay, it would drop to, say, 95 degrees. Well, why is that important? Some of those other chemical reactions at different temperatures change, which then means we get different products coming out of it.
So how can
Okay.
you use standard boiling point for elements if it changes?
Which is a really important point. If we look at an individual element, we can look up and report boiling points. How could we have a standard boiling point if the boiling point changes with your elevation?
Pick a specific point.
You don't.
It's generally.
When you look at a boiling point, if you found a proper boiling point, you almost always will see written next to it
At sea level.
the pressure at which the boiling point was obtained. You have to specify both, because if you change the pressure, what happens to the boiling point?
Changes.
It changes. So you have to have both pieces. So when we talk about 100 degrees Celsius for water, that's 100 degrees Celsius is the boiling point for water at a specific pressure. What is that specific pressure? Standard pressure.
Where's
What
the
is
standard?
standard pressure?
Where's it?
Okay, we pick it at sea level and it's defined as 1 atmosphere. Okay, and we'll look at what that pressure is. That's ultimately a measure of our force. Okay, so 1 atmosphere, and we said pressure doesn't change that much. Did temperature change a lot? Yeah. Okay, but arguably within a room, temperature doesn't fluctuate that much. Right? You may walk into a lab and go, ah, this is cold, or walk into another room, oh, this is a little bit warmer. But how much is the temperature really changing there? Like 5 degrees Celsius at most, and that's a pretty significant swing. So maybe standard temperature isn't that big a deal. What is our standard temperature? So room temperature, right? That makes sense, because that's where we do our experiments. Room temperature, which is ballpark 20 to 25 degrees Celsius. What is standard temperature? Zero. 0 degrees Celsius. How many of you are going to do an experiment ever in your life at 0 degrees Celsius? So we're having you memorize a conversion factor for a gas that you'll never work with, okay, at a temperature that you will never experiment at a pressure arguably is questionable but might be somewhat standard. Why?
Is there a place that actually is at sea level with one at a temperature?
But you can't-
Yeah, which is going to be a whole other thing. So how do we end up using this? We use this because this is tied to what? Big hint, there's a word right at the top of the slide.
Yeah. Behavior.
Before that,
Ideal.
ideal. In the ideal world, when I run my experiment on gases, okay, it will be at 0 degrees Celsius and at 1 atmosphere. All of those conditions, stars align, everything comes together perfectly, now this equation works. How often do we expect you to use this? A freaking lot. Okay? That's why it shows up in chapter 8 before we talk about molarity. Okay? So this conversion factor is expected for you to use a whole bunch of times. Why? I have no clue other than to say it is a conversion factor, and we decided that you needed to memorize more useless facts. Anybody get an idea? I'm really not a fan of this. Just a little bit. Okay? We will talk about where this comes from, because where it comes from is important. Okay? That should be memorized. This should be burned from, burning books is a bad idea. Should never say that. This should not be presented in this fashion. Okay? But it comes down to, well, we could say that students learn something because they memorize this 22.4. You didn't learn anything, you just memorized a number. Okay, I can do that too. 6. Okay. So, sorry. Breathe. Gas exerts a force. That force is known as pressure. Okay? So, because we have this conversion factor, we have to now manipulate it and use it. So guess what we get to do on our very next slide? We get to do a conversion. So this is the fun one. See, let's just go straight into this. This is straight, by the way, straight from the textbook, not completely unadulterated by me. How many liters are needed to hold 2.0 grams of hydrogen gas? Okay, so let's attempt to solve this. What are we solving for?
Liters.
Wrong. What are we solving for? If it makes you feel better, you notice I did write the capital L. What are you solving for?
Liters of hydrogen gas.
Liters of hydrogen gas. Units require full things. So measurement and substance. What are we starting with? I'm not going to be happy with 2. Grams of hydrogen gas. What is the symbol for hydrogen gas? H2, because it's diatomic. How many grams? 2.0. Okay. Ideally, what do I do? Well, number one, is grams of hydrogen the same as liters of hydrogen? No. So what do I need to do? Convert. What am I converting? What is grams or liters as a class? They are the measurement. I'm trying to do a measurement conversion. Ideally, I would do grams of hydrogen to liters of hydrogen. Come on, ideal. Liters of hydrogen, right? I want to do it in one step. How many of you want to do it in more than one step? Yeah, see, nobody raised their hand. Right? We want to do it in one step. Can we do it in one step? No. Okay. So what do you want to convert grams to? Or liters to? Which one do you want to do it? Grams. Why do you want grams? Cancels. Okay. What do we want to convert grams to? Why moles? Right? So, and the why is an important question, and you should always be asking yourself that. Okay? One of the answers to that why right now is, when do we use moles? Virtually all the time. So what would be a good first step? Convert it to moles. Okay? I disagree with that because that's not following kind of the fundamental of our unit conversions, but it's a legitimate first step. Okay? So we could work with that. Where's the conversion factor between moles and grams found? Periodic table. So we go to the periodic table, and we would find 2 what?
2 grams of hydrogen.
Officially 0.2 grams of hydrogen is 1 mole of hydrogen. This is something that I will try and watch for when writing your exams. I make sure that I account for those sig figs appropriately. Okay. Is moles of hydrogen the same thing as liters of hydrogen? What do you need to do? Convert. In that conversion, what do we hope to happen? Moles of hydrogen disappears, and what do I want? Liters of hydrogen. Is there a conversion factor that exists? What is that conversion factor? 1 mole equals 22.4 liters for a gas at STP. Is this a gas?
Yes.
Okay, cool. Is it at STP?
They don't know.
We have no clue. This is why it's frustrating. Okay? I did not edit this question. This is exactly how the textbook presents it. What are they making the assumption of? That it is at STP. That should be explicitly stated in the question. Because if it is not stated in the question, does that conversion factor work? No. Okay, so that's why it is very, very important and why I get particularly irritated about it. So, we're going to say at STP now. Now that we have that information, what can we go through and do? 22.4 goes with liters, 1 goes with the moles. What happens to our units? Moles of hydrogen cancel, what do we have? Liters of hydrogen, is that what I was solving for? Yes. Okay. How else could the question get written to make sure we were at STP? We could say at STP. Well, we had that one up there, so I want a different edit. We could say assumed STP, yeah? Ideally STP. Um, 0 degrees Celsius standard temperature? Yes. There's 1 atmosphere standard pressure. Yes. It could get written out longhand, and that tends to freak students out a little bit. I would argue that's better than writing STP because we can use that. Okay? We could also have written it well, that's certainly not STP, right? That's not standard temperature. Standard temperature is 0 degrees Celsius. But Kelvin is degrees Celsius plus 273. You'd have to remember that temperature conversion. Okay? Make sense? Okay. Just because it happened to flash, I've got more anger to unleash about STP. My wife is a process engineer. She does stuff with gases all the time, gas phase reactions, all sorts of crazy stuff. They were trying to figure out why their system wasn't working properly, so she went back to calculate the flow of the gases, determine how much gas was present, how was the reaction working, all this fun stuff. She went back to do all these calculations and ran through the system and was like, I'm not getting what our system says should be matched. And then she came to me and she said, oh, you're a chemist, you're supposed to know this. And, yippee. Okay, so we sat down and we went through it. I got the exact same answer as her. Didn't match. I'm like, I don't know what to tell you. Like, these calculations are right. Whoever built the instrument is doing something weird. Right? An engineer built the instrument. An engineer thinking in the non-science realm, in the reality of the world realm, said that a good standard temperature would probably be room temperature. So when they said their instrument was calibrated to standard temperature and pressure, their standard temperature was different. Standard temperature and pressure changes depending on the field you're talking to. It is insanely frustrating to reference a conversion factor based on a standard that is not standard.
Aviation standard temperature is 15 degrees Celsius.
I find it so freaking frustrating. Was it in a clean room? Yes, it's in a clean room. The temperature is always constant. That doesn't mean it's 0 degrees Celsius. And because you're looking at a gas, if you change the temperature, what do you change? The energy of the particles, which changes how your system reacts. So yeah. All she had to do was change the temperature. All of a sudden it worked. Everything came out and matched. It was, yeah. Exciting. So, the other thing we can go through and do, how many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid? See what you can come up with in 4 minutes. Okay, so if we look at the question, as we stated but didn't record, we should make the assumption it's at STP to go ahead and solve this one. So we'd go through and start, is grams of aluminum the same thing as liters of hydrogen? No. So what do you notice? Okay, so that conversion factor doesn't exist, but what things have changed beginning to end? The substance and the measurement, both have changed. Okay, so now it's going to come down to focusing on which do you want to evaluate first. Do you want to evaluate the substance or do you want to evaluate the measurement? That's entirely up to you. Okay, I heard measurement at first, so if we're going to change the measurement, we can't change the substance, so it has to stay aluminum. What substance do we, or sorry, what measurement do we want to convert it to? Why moles? I gave you an easy cop-out earlier. Because we always need moles. Moles are useful, so we could just go to moles. Okay. The slightly less of a cop-out is, did the substance change? To convert a substance, what do you need? You need moles. We need a chemical equation and the unit would need to be moles. So convert to moles because the substance is changing. Okay? That is a slightly better explanation for why we should convert to moles instead of just saying, well, we should. Where do we find the conversion between grams and moles? That's on the periodic table. And so for aluminum, it would be 13 grams is 1 mole. It's 26.98, but doesn't aluminum have 13 next to it? What is the 13? The atomic number. What are we looking at? The mass. Is 13 the mass? No. What do we have to look at? 26.98. Okay. You have to remember you can't just pull numbers randomly. You have to know why you're pulling those numbers. Okay. We would now have units of moles of aluminum. Is moles of aluminum the same thing as liters of hydrogen? Nope. So what do we have to do? Convert. In this case, we're hearing a suggestion for the substance. We can't convert the measurement unit and the substance, so we'll deal with the substance first. Moles of hydrogen to moles of aluminum. Where do I find that conversion factor? The balanced chemical equation. The balanced chemical equation is a little bit tricky to solve because we get that H2, which makes it a little bit more challenging. You will probably have to cycle through this one a couple times to get it to balance. Okay? As long as you're still changing numbers and you don't feel like you're changing cyclically backwards, keep going. Okay? If you have to cycle through your balancing process like 5, 6 times, then you've probably made a mistake. Okay? This one, I think you should hit 3 balance attempts before it actually balances. The 4th one should prove that you did it right. Okay? And we would pull the coefficients from the balanced equation, which would be 3 associated with the H2 and 2 with the aluminum. Is moles of hydrogen the same thing as liters of hydrogen? Where do I find the conversion factor between the moles and the liters? This is from your brain. When is that conversion factor valid? For a gas at STP. Right? And we know 22.4 liters is equal to 1 mole. Okay? We're kind of out of time, so we'll talk through a little bit here. One thing I do want you to watch out for. I could list standard temperature and pressure, making you think that equation or that conversion factor was valid. But I could say solve for an aqueous solution. Would that conversion factor be valid anymore? No. But you're picking up on the STP and immediately assuming that that works. It only works for a gas and STP. Both of those conditions must be true for that conversion factor to be valid. Okay? We'll talk about atmospheric pressure and the rest of our gas law stuff on Thursday.